Hello and welcome. In this lesson, we'll learn about algebraic vectors. We'll answer questions such as, what are algebraic vectors? Why do we have to study them? And then we'll look into algebraic vectors in both 2D and 3D, which we also call R2 and R3. And we're going to take a look at how to operate with algebraic vectors, like find the magnitude, add and subtract algebraic vectors, and then multiply them by a scalar. So far, we've looked at vectors and we said that a vector is this pointed line segment and it has a tail and a head. And we've been talking about two main things about a vector. Number one, the length or the magnitude of the vector, which is usually described by the length of the line segment that represents it. And number two, the direction of the vector. And whenever we talked about the direction of the vector, we described it as the angle that this vector might make with some other vector that lie on the same plane. So the angle made between vectors A and B. And we said that if you place them tail to tail, they will make an angle, which will tell us in what direction one vector is pointing in relation to the other. So say, for example, vector A is making a 20-degree angle with vector B, and that was it. Now, these type of vectors that lie on a plane are what we call geometric vectors. Now, once we place these geometric vectors on the Cartesian plane, then they are called algebraic vectors. So that's what an algebraic vector is. Simply a vector that lies on the Cartesian plane, and it can be anywhere on the Cartesian plane. Now, think about it this way. If I were to ask you to draw an algebraic vector, a specific algebraic vector, what information would you like to know about it so that you'll be able to draw the vector as described, the vector required? So I would say that in order to know exactly what vector to draw, I would need to know where the vector starts and where the vector ends. So in other words, you will need to be given information about the coordinates of the tail and the head. So this one here would be the coordinate XA, YA, and the head will have the coordinates XB, YB. So we'll say that for an algebraic vector, we're going to need to know the coordinates of the endpoint, or the coordinates of the head and the tail. And once we know what the coordinates of the head and the tail are, then we'll know exactly where the vector is located, what the direction of the vector is, and what the magnitude of this vector is. So, and this is the power to using algebraic vectors. Just by knowing the two coordinates, we know everything about the vector, the magnitude and the direction. Now, very often, these algebraic vectors, for convenience in communication and solving problems, are brought down to have the tail planted at the origin of the Cartesian plane. And that will help us identify the vectors a bit more easily. Because the tail now is at 0, 0, and this is what we call a position vector again, and I'm going to change the color of it so that we can color code things around here. So this is a position vector now, which is basically an algebraic vector that is placed in a special position, and this is algebraic. So remember that a position vector is basically an algebraic vector placed with the tail at the origin, but an algebraic vector is not necessarily a position vector, right? So it only has one name. However, it is worth mentioning that every algebraic vector has a respective position vector. Now, let's talk about the position vector. What would be the information we need to draw a position vector? Just the word position entails that the origin will be at 0, 0. So we'll know right away that the tail would be, or the coordinates of the tail are 0, 0. So all we need to know about the position vector is the coordinates of the head of the vector. So if we're told that we're given the position vector, let's say, for example, OP, then all we need to know is the coordinates of one point, or a set of coordinates of one point, which is the heads. Now, how are the coordinates of the head of the position vector related to the coordinates of the respective algebraic vector? So for this, what I'm going to do is play with numbers, because numbers are easier to see. And as you can see in here, the point A will have the coordinates 1, 2, 3, 4, 5, negative 5 here. And for the y coordinate here, we'll have 1, 2, 3, 4, 5, 6 here. So A will be negative 5 and 6. And B, on the other hand, will be 2 in here, and this is 6 is going to be for the second one. Sorry about this. Here we go. So this would be 2 and 6. And this one here will be 2, and for A, we have the coordinate 4. Okay, so when you look at the coordinates of the position, the respective position vector, you can tell that the respective position vector will have the coordinates x equals 2, 4, 6, 7, and y equals 2. So 7 and 2. So compare the the x coordinates of points A and B. So from negative 5 to positive 2, there is 7 units in between, and that's why we have the x coordinate of the head 7. So algebraically speaking, or the calculation that we're going to use more often is 2 minus negative 5. So in other words, for the position vector, which we called OP, the coordinate of the head, the x coordinate of the head, was x at B minus x at A. And the y coordinate, which is 2, let's take a look at the y coordinates of A and B. So for A, we have y coordinate 4, and for B, we have y coordinate 6. For the position vector, the y coordinate is 2. So 6 minus 4. So the difference between the y coordinates, yb minus ya. So if we are given an algebraic vector, and we're described the algebraic vector by both coordinates of the tail and the head, then the respective position vector will have the coordinates xb minus xa, so the x at the head minus the x at the tail, yb minus ya, so y at the head and subtract y of the tail. So let's take a look at our summary, and I wanted to go over all we talked about so that we can understand the summary better and be able and have interest in following it. So any geometric vector, when placed on the Cartesian plane, is considered to be an algebraic vector, we said. Algebraic vectors can be located anywhere on the Cartesian plane. Every algebraic vector has an equivalent position vector, which we created by simply sliding the algebraic vector with the tail at the origin. Position vectors can be uniquely identified by the coordinates of the tip or the head of the vector or the end point. And if these are the coordinates of the head of the position vector, and A, x1, y1, B, x2, y2 are the respective position, are the coordinates of the head and the tail of the algebraic vector, then the position will be x2 minus x1, y2 minus y1. So, if we have a position vector xy, we say that the horizontal component or the horizontal coordinate x is x2 minus x1. Vertical component or the y coordinate is y2 minus y1. So when you think about the magnitude of the position vector, and we can go back to our diagram in here, Remember that the position vector serves as the hypotenuse of this right angle triangle here. Now, having this as an x-coordinate, which will define the length of the base of this triangle, and this will be the y-coordinate that describes the other side of this right angle triangle. This is right angle. Then we'll say that the length of the vector OP is x squared plus y squared inside square root, using the Pythagorean theorem. So in other words, we say that OP has a magnitude of equal to square root of x squared plus y squared, with x being x2 minus x1, y being y2 minus y1. Then the magnitude will be the square root of x2 minus x1 squared plus y2 minus y1 squared. If we want to know the direction of a position vector, then we look at the angle that is made with a positive x-axis all the time. So let's go back to our diagram again. So if we want to know the angle of the position or the direction of position vector, we look at this particular angle, call it angle theta. Now angle theta will have on the opposite the length y, and as adjacent the length x. So we use the tan ratio to find the measurement of angle theta. So this is where this comes from. Theta will be inverse tan y over x. And with y being y2 minus y1 for the respective algebraic vector, then we can rewrite or write the other formula which applies to any algebraic vector. Now, another very important concept that we need to use very often when communicating with algebraic vectors or position vectors is the unit vector. So a unit vector is a vector that goes of a magnitude of 1 unit, and it follows the direction of the axis. So we have a unit vector for x and a unit vector for the y-axis. Now, the unit vector for the x-axis is called unit vector I, so indicated by letter I. And that is all the time, it's not a choice. And the unit vector for the y-axis is called J. Their magnitudes are exactly 1. Now, remember that there are two forms of expressing the algebraic vector. In component form means that we're just describing the coordinates or giving the coordinates of the head of the vector, negative 3, 2. Or in what we call the standard form. So standard form is when we use the unit vectors I and j. So remember that a vector is given, any vector is described or can be given as the sum of two other vectors. One will be the horizontal and one will be the vertical component. So if you use the parallelogram rule in here, so this particular vector, which I am going to call vector AB, will be the sum of the horizontal component times the vector I, which is a direction vector, plus the vertical component times the vector j. So that's what gives, so this is kind of, the standard form is like the vector way of describing a vector. And the component form is the Cartesian plane way of describing a vector. You can put it that way. So the new terms that we should understand by now are algebraic vector. Do we know what that is? Any vector placed on the Cartesian plane. Position vector. Well, algebraic vector with a tail at 0, 0. Vector magnitude. That means the size or the length of a vector. Do I know how to find? Wait a second. Here is a formula for it, right? So what else did we learn? Vector direction. How do I describe it? Think about it. Well, I describe it by using the angle the vector makes with a positive x-axis. Again, when vectors are placed in standard position or position vectors. Component form. This is the component form of a vector. Oops, that wasn't supposed to happen. This is the component form of the vector, and algebraic form of it is, the respective algebraic form is this one. So now that we know the language of all the terms that we're using in when operating with algebraic vectors, we are going to learn how to actually work with algebraic vectors or operate with them. So let's take a look at example 1. We are given algebraic vector AB as indicated on the diagram. So we have some vector here, so I assume that this would be A and this would be B then. We have to identify the coordinates of AB. Oh, that's easy. So I've done this in elementary school. That's -3 here, and we have 1, 2, 3, -4. So I would say that point A is -3, 4. Point B, on the other hand, has the coordinate x equals 2 and y equals 1. So 2 and 1. Now I have to find the coordinates of the respective position vector. Okay, let's do this. So I will draw the vector here, and I will slide it over. And can do this thanks to this app. Not that I'm that good at it. Okay, there we go. Here we are. So this would be the respective position vector. I'm going to call this vector OP. And we need to find the coordinates of P. So let's do this. So P will have the coordinates x equals 5 and y equals 1, 2, 3, 4, 5. So we'll say that OP will have the coordinates 5, 5. Now we have to find the magnitude of vector AB. Now think about it. Vectors AB and OP, since OP is the respective position vector of the algebraic vector AB, will have the same magnitude. Which one would be easier to find the magnitude of? Would it be OP or AB? So I hope you chose OP. So we're going to say that the magnitude of AB is the same as the magnitude of OP because algebraic, respective position vector of that same algebraic, right? So that would equal the square root of 5 squared plus 5 squared. So that would be the square root of 50. If you simplified it, that would be 5 square root of 2. That's how many units the magnitude is. Now we have to find the direction of AB, which means that we have to find the angle that the respective position vector of AB, which is this one, will make with the positive x-axis. So this is the angle we're looking for. And we'll say that, oh, we're trying to find angle theta. So that must be inverse tan y over x. So that would be inverse tan. And we're going to say 5 over 5. Or inverse tan of 1. Which equals 45 degrees. So we'll say the magnitude is 5 root 2 and the angle made is 45 degrees. Now let's take a look at another example. We're given 3 vectors, V, R, and W, and they're drawn here for us. And we have to find their magnitudes and their respective directions. So I'll start off with giving them a name here on the Cartesian plane. So we have the vector V, 2, 3. We have the vector R, -2, 0. And vector W, 3 and -2. So that's W, V, and R. Okay, so we have to find the respective magnitudes and directions. I'm going to start off with V. They're all angles in standard position, or they're all position vectors, we say. And we'll say that vector V equals the magnitude of 2 squared plus 3 squared. So that makes V equal to 4 plus 9 root 13. Magnitude of vector R is the square root of negative 2 squared plus 0 squared. And obviously we can find the magnitude of R just by looking at the diagram here, because it makes an angle 180 degrees with positive x-axis. And vector W will have the magnitude 3 squared plus negative 2 squared, which is 9 plus 4 root of 13 again. Now we have to find the angles made. So I'm going to call the angles alpha, alpha, and then I'm going to call angle that vector R makes with positive x-axis angle beta, and the angle that W makes with a positive x-axis gamma. So I'll start off with alpha. So that would be inverse 10 y over x, which is 3 over 2, so x and y here. 3 over 2, so just use a calculator for it. And then we'll get, give me a second. So make sure your calculator is set to degree most of the time. We use degrees, so inverse 10. We said 3 divided by 2, which gives the angle 0.98. Okay, so I made the classic mistake of forgetting to convert to degrees. So again, inverse 10. Sorry about this. So I got 56.3 degrees here. Now for angle beta, we're going to say that's inverse 10. And the y coordinate is 0, x coordinate is negative 2. So again, inverse 10, 0 over negative 2, which is basically inverse 10, 0. And that gives the angle 0. Now, as you can see, vector R doesn't make an angle 0 with the positive x-axis. So this is when we use our trigonometry knowledge, the knowledge from trig, and think, okay, so the reason why we got angle 0 from the calculator is because the calculator will always give you the smallest angle that has the tan ratio equal to 0. But we already know that the location of vector R is in the on the negative x-axis. So we're going to say that the angle beta is 180 degrees. And last but not least, we'll do W. So angle gamma equals inverse 10. For W, we had negative 2 over 3. So let's check and see what we get for W. So inverse 10, negative 2 divided by 3. And in this case, we got the angle negative 33.7 degrees. So usually we express the angles in positive numbers, using positive numbers. And obviously, again, the calculator will give us the smallest angle made with the horizontal axis. And that's the angle the calculator will give you, negative 33.7. But we'll say that the angle gamma is 360 minus 33.7, and that equals 326.3 degrees. Now we're going to take a look at one last example with vectors on 2D. We are given 3 different points, A, B, and C, and we have to find each vector. So I'm going to plot the points. We're going to start off by plotting the points first. So point A is 2 and 3. So x equals 2, y equals 3. point B is -1 and 4. I think we can go by a scale 2 squares, 1 unit, because it seems that we're a little bit too tight if we let it 1 square. Okay, and x equals 2, y equals 3 will be point A right here. Point B is -1, 4, x -1, and y equals 4. Sorry, here. And last, we have 0 and -3. So x equals 0, y equals -3. So that would be point C. Now we have to find the vector AB. So I'm going to draw vector AB first. So AB means that we're starting at A and ending at B here. So it's pointing at B. And the coordinates of AB will be x at B minus x at A, YB minus YA. So remember that this is XA, YA. If this helps you, go for it. So write down the name of each coordinate. So XC, YC. And substitute. So y at B is 4 minus 3. X at B is, we're doing x first. So -1 minus 2. And y at B is 4 minus 3. So that means that vector AB is -3, +1. So what that means is that if we were to create the position vector of AB, which means the tail at the origin, then the position vector must have the coordinates -3 and 1. And let's check it out. So our answer is right, because it does seem that this vector has the coordinates -3 and 1. Now let's do BC in a similar way. So we'll have for AC, I'm going to make this red. Start at A and at C. We'll say that we have XC minus XA, comma, YC minus YA. So X at C is 0, A is 2. So 0 minus 2. Y at C is -3. Y at A is 3, so -3. So it seems that we have the coordinates -2 and -6 here. And again, we're going to try to do the same thing because I want to check and see if my answer is right. So it seems that we are outside of the grid in here, but you can tell that for the x value, we are about at -2, and the y value should work as well, right? So last, again, in the exact same way, we'll do the vector BC, which is going to be XC minus XB, YC minus YB. So X at C is 0, and X at B is -1, so minus -1. Y at C is -3, Y at B is 4. So this would be 1 and -7. So let's draw this vector. That's vector BC, so start at B and at C. Right here. And voila, these are the coordinates of each vector. And obviously, whenever we state the coordinates, we find the coordinates of the position, the respective position vector. So I hope that you found the instructions useful. I know that the lesson is a little bit long, but we are trying to look into each and every detail and not get lost in the whole process. So thank you for listening, and bye for now.